right. Well, spacecraft subsystems. Hopefully you know what a satellite is by now. A satellite is.
Put the mic on your shirt.
I'm sorry?
My mic on your shirt.
I can put the mic on my shirt. Like that?
Yeah,
Okay. All right. As long as everybody knows what a satellite is, it's nothing more than a vehicle going from point A to point B. It just does it in a circle or ellipse at this point in orbit. Other times we send satellites to other planets, so it does go point A to point B, impactors and so forth. So they are just a vehicle, and you develop them likewise. The only difference is we send them in a little bit different medium than what you do with your cars and everything around on the planet Earth. So we send them out from a atmospheric level, 1 atmosphere down here near sea level, and then send them out into space, which goes into a hard vacuum, or worse, into a hard radiation environment, something that we don't encounter as living organisms down here. So as you develop something, you know, we have this neat thing called engineering that allows us to go in and optimize these devices while they, you know, condition them for their environment before they go. So within the design space, everything is about launch, orbit, and destruction of whatever it is, whether or not you re-enter or anything of that sort with a satellite. But in the end, satellites can be developed and are much like everything we have on Earth: cars, UAVs, airplanes. That's why a lot of our universities teach aerospace, so a combination of satellites and aircraft, and some automobile even, because it's optimization of lightweight, fuel efficiency, dynamics, environment. So perhaps the most similar are UAVs. And that's actually where I started. My career was with UAVs after I graduated in mechanical engineering. And so if you look at UAVs, you can quickly pick out similarities between two. Up there top, you have a Global Hawk UAV, which is produced by Northrop Grumman. It's one of those high altitude versions that flies up around 60,000 feet and does surveillance. And then on the bottom there, you have the Milstar satellite, which was produced in the 1970s by Boeing and just about every contractor on the planet, and provides telemetry and control for, it's basically the backbone of our military still. It has about 20 kilobits or so of data per second. It goes into the front lines of all our military and so forth. But you quickly can pick out what is common. In the Global Hawk there, in the nose of it, you have a big dish for the comlink, high gain up to Milstar actually. And Milstar likewise has very high gain antennas down to the Earth, to the control stations, and then a whole bunch of simple broadcast antennas down here for individual spot beams. So, you know, a Global Hawk UAV flies through the atmosphere, so it has a big wing, so wing loading matters, altitude, and a nice propulsion device right there. Unlike our Milstar, which is big solar panels and very minimal thrusters, even though there are some on the corners there. That's just for station keeping. So Milstar is up in geo, so it doesn't have to do too much up there. It's very far out. So similarities are, both of them are super lightweight. Everything is optimized for that. This one, of course, is made for going through the atmosphere. This one doesn't care so much about drag. So it's much more cumbersome, you could say. Not as pretty, right? However, in the end, they are just two vehicles. And once they're launched, you can never touch them again. So when you do launch them, you have to make sure they're nearly perfect. We wish. Anyway, they are completely remotely operated at all times. If they die, well, the Global Hawk will eventually come back, hopefully. But in the end, they're what we call a 6 DOF environment. They're free body. Have you described anything with 6 DOF? Okay. If you throw an object into orbit, there's nothing that says that you can't rotate the body about any axes. So there's 3 axes usually. Phi, theta, psi. Then the other 3 degrees of freedom, of course, are position, translation of position. So in orbit, you're going around a very fixed kind of racetrack. With a UAV, you may be flying from the United States to Europe. But both of them are free body in that they do not have a direct tether to the ground, like a car does. So a 6-DOF environment is very important to learn about and very complicated, which in some of your next, if you get to the dynamics class here in about 2 or 3 years, you'll learn all about it. But in the end, they're remotely operated, which means you have to go over a comm link. Has to be RF. Some do optical nowadays, but in the end, RF is the way to go because it's so robust. So with a remotely operated platform, you need a radio and a payload. The whole idea with the Global Hawk is to go out and observe things with a camera, zoom in, or with the radar. Likewise on satellites, we put cameras, we put star trackers. Hubble puts a big camera on it to look at stars and galaxies and so forth. So in the end, this is a satellite right here. Just 2 subsystems in theory. We have to put a hodgepodge of other subsystems on them, of course. So we'll go through each one of the subsystems here, starting with payload. The whole reason that you launch your satellite is the most important. If you don't have a payload, you don't really have a reason to have it. So we always put all other subsystems in support of the payload. In that case, power, communication. We manage the waste coming off the payload. We manage the environment of the payload. Here's the example of CXBN in the lower corner here. Make sure you have enough. And the payload, of course, is the big CZT detector, trying to detect 10 kiloelectron volt to about 100 kiloelectron volt X-rays. Do you know, everybody knows what CXBN is, I hope? All right. So, that is the block there. What we consider kind of second-tier subsystems are those supporting things, but they're still so important in that they maintain the link to the comm link or have some very important aspect to them like power. So if you don't have those 2, you wouldn't be able to make the payload even operate. So second tier is there. We have our little radio board highlighted. Those are the batteries, and that's the EPS. So all right there are the very important guys of radios and power. Everything about it is integrated, of course, and likewise in bigger satellites, you have individual blocks. They're actually plugged into the satellite, much like in a car. You see the electronics module that controls the engine. Same sort of thing, bunch of wires between the 2. On the power side, we have, with CubeSats, it's all solar, but in NASA missions that go out beyond Mars, you know, Mars only has about 1/3 of the solar energy as Earth. So you'd have to launch a 3 times larger solar panel for going around Mars than you would in Earth. You go out beyond Mars, there's not enough solar energy to run anything. So that's why they all go nuclear out there. So RTGs. There's some mechanical storage with reaction wheels and gyros and flywheels and chemical, of course. Everybody puts a big rocket engine on all of them. And then there's the quasi, photoelectric and electric ion thrusters, which are still kind of, they're good, but they aren't enough to provide a delta V to send you to another planet. Anyway, so second tier is radio and power for subsystems. Third are all those other things, pretty much. Propulsion, navigation, the peripherals, the data that's coming out, and waste heat. They're highlighted there. We have the Star Pepper, and it was to detect the phase of the spin rate of the vehicle. The CNDH with the IMU on it there, and the magnetorquers. All of those things do something to control the 6-DOF behavior of the satellite. to control how the payload orients itself or does something. So we kind of consider those more third tier in that they are subordinate to the other subsystems in their importance. Any questions so far? None at all? Am I going over your head too far? Okay. Then we'll continue on. Here's the payload for CXPN. If you haven't seen it before, a CZT block with a high voltage feed off the top, that little circular thing, and there's a little wire that goes across. It has a little readout on the back end. It has an SPI interface. Does everybody know what SPI means? Everybody in my class should know, I hope. Serial peripheral interface? Yeah? Yeah, yeah, you better. It's all packaged up into a graded Z shielding. This is actually lead, and then underneath is copper, and underneath that is tin. And then packaged up, it looks like that. So you can quickly see what a payload is. Turns into quite a chunk of metal after all the engineering is done in order to support it. So in satellites, that whole process is where we get our jobs. On the comm side of things for CXPN, this little module was a UHF radio. Yeah, there's not much to say there. Does everybody know what a dBm is? RF output power is usually labeled in watts, dB watts, or dBm. 31.5 dBm is 1.5 watts. So dB is a log scale, and so a doubling of a quantity is equal to 3 dB. I recommend reading about it on Wikipedia or whatever if you need to brush up on that. It's something we use a lot around here, and you will continue to use it through more courses. Have you learned anything about modulation techniques? None at all. You'll be running across it. Gaussian frequency shift keying, GFSK. There's BPSK for binary phase shift keying, BPSK. QPSK, quadrature phase shift keying. QAM, quadrature amplitude modulation. All kinds of others. With our radio system, we set it up to run a beacon so that you could get data from the satellite without having to command it to send you something. And all kinds of other little things that we provided a bootstrap loader entry into the main processor so we could reprogram the satellite as we went. So, example of another supporting thing are antennas. We're just going to go through each one of the subsystems here. In this case, it's quad monopole. Each one of them is phased at 90 degrees to another to provide a right-hand circular polarized RF field. You'll learn more about that here in the next year or so. We put that in the anechoic chamber, of course, ran it through network analyzers also to tune them so that the performance would be okay. And this little thing down here is what provides the phase shifting. You'll learn about that more in the future. Any questions so far before we go to the next one? Any curiosities? No. Okay. EPS, everybody has seen Eric running around building solar panels, I hope. He tabs all of the individual cells and puts Kapton tape down, and each one of our solar panels is plated in gold to help with the thermal aspects. This was a CXPN panel, of course, and there's more. These are the lithium 18650 batteries, same thing that you have in your laptops. A very standardized cell. Okay. EPS side, if Ken were here, I'd bash him on this one. EPS-wise, we created a 2-layer EPS that sat right below the batteries, that little green board there. 2 green boards, actually. And it regulated all of the voltages necessary for the satellite, 5 volts and 3.3 volts. All kinds of neat little bells and whistles in order to turn things on and off remotely and detect current and voltage and so forth. But in the end, has everybody learned about charging methods of batteries in space? Okay. Direct energy transfer is whenever you hook up essentially a diode. Current flows from the solar cells to the batteries and just kind of goes over a waterfall of a diode and doesn't go back out. Right. There's other things called maximum power point tracking, things like that, that are used for more efficiently collecting solar energy, but they're very, very complex. And if Ken were here, he'd tell about his 12 revisions. It only took me and other students 7 revisions. All right, CNDH-wise, this is the CNDH from the CXBN. This is the IMU from Analog Devices. This is the little MSP430. It's 5436A. A little programming port, and then I didn't put the rest of the cables on this picture. But there's some flash to store data. Each one of these plugs over here was for the magnetorquers. Power data to the payload, to the radio, to the power system. But the very important thing, because we launch these things and we can never touch them again after they go up, you really have to make them reprogrammable from the ground. So you try to make a direct link from your radio to your CNDH so that you can change the way your satellite goes or behaves on orbit. You know, NASA has completely converted their way. They used to make everything as a kind of a one-shot, kind of like the Voyager series spacecraft, those two. They just sent them out, they programmed them one time, that was it. Every mission now going to Mars doesn't fly with software in place. It flies with a bootstrap loader. And then they load the flight software about halfway there because they don't have enough time to finish the flight software before it launches. It takes a long time for software, especially the way they do it. They do it in the very reliable method. Yeah, it's very interesting. It's also a different kind of engineering that happens. So the management teams and the engineering teams stay in place for 2 times longer than they would normally.
How long does it take to get to Mars?
Minimum time is what, about 3 months. Other times, I think some of the longer ones are upwards of 6 to 8 months, depending on how far away it is at the time. It has a 2-year cycle, I believe, 2 or 3 year cycle for that minimum time of 3 months. Okay, so BSL means bootstrap loader. That's what the entry provides BSL entry to the payload and the EPS. Reprogrammable. LQFP stands for low quad flat pack. That's the processor type right there. That little dot right there, that's the secondary dot. That dot right there is pin number 1. 100 pin package for the LQFP that goes down there. DMA for all the UARTs, 3 to 16-bit timers for our magnetorquers. And this doesn't have any arrows, but it's supposed to show arrows from the subsystems. The pepper went into the payload goes to CNDH, the power goes to CNDH, spare goes to CNDH, sun sensor goes to CNDH, IMU goes to CNDH. The magnetorquers go over to it, so basically this one processor was everything for this satellite. But it still is only considered second tier because the payload was the most important. All of these things support the payload. ADS, Attitude Determination System. Pitch and yaw were determined with a sun sensor. This is a medium field sun sensor, about plus or minus 15 degrees, and this is a fine field sun sensor, which is about plus or minus 5 degrees. This was built up by Luke Lim, if you have met Luke. I'm being recorded, right? More ACS. The magnetorquers are a air core. Just wind up a coil of wire, run some current through it, creates a magnetic field, magnetic dipole, which interacts with the Earth's magnetic dipole, and you get a torque, M cross B. All right. How do you do that? You can't just put a DC voltage on it. You know, you have to be able to toggle it on and off very quickly so that it looks like you have varying levels. And that's what we use pulse width modulation for. Just like servos on your RC cars, those are PWM operated. If you have, did you guys do that? Okay. Did you describe what duty cycle and period of the PWM was? No. Okay. Well, PWM pulse width modulation has a duty cycle frequency, and based upon that, you can achieve different voltages and currents across your coil. In that case, it was a little coil across another permanent magnet, which made your little servo run. In this case, it's the Earth's magnetic field that interacts with this dipole you create with this coil of wire. So there's a little connector. It has a little H bridge right there. All of it's epoxied down to help dissipate the heat. There's quite a bit of heat that's generated in here. 1.6 times 10 to the negative fourth Newton meters of torque. Tiny. It's like literally a needle in a compass. You know, they always have to make them on a little pin. That's how much torque you're really getting on this satellite. It's not the same as a car, you know, torque, 300 foot-pounds of torque or something on a car. This stuff, once you're up in the environment of space, it takes very little amounts of force to make your body spin. It takes very little.
So that is enough to make for all you need for
Yep.
for that.
Yep. You also don't want to put too much on. You know, if you have a piece of space debris come and hit your satellite, it'll quickly tumble out of control. Very quickly. So everything you want to put minimal amount of force on it to provide any type of upsetting, to reduce any type of upsetting moment, and do things very slowly, because the implications of you doing something too quick are disastrous to the mission. All right. There were 3 of these packed inside of CXBN. The structure, I'm sure you guys have seen this. It's black anodized. Actually, I think they called it gunmetal gray or something. But only a portion of these rails is required if you go look at the CubeSat standard. Has everybody looked at the CubeSat standard here? I hope. Good. It says that the rails must be anodized, and also an RBF pin and foot switch and so forth. Aluminum, there's all kinds of different grades of aluminum out there. They were all created back in the 1950s, 60s, 70s for aircraft. In this case, the most used one is the 6061, tempered to a T6. If you are interested in materials, there's all kinds of books out there for metallurgy. Type 3, gunmetal gray, anodizing. Anodizing, does everybody understand what anodizing means? Nope. It means non-conductive. Allodyne, when you allodyne something, it becomes conductive.
How do you go about anodizing?
Okay, so you put it in a hot salt bath. There's a couple of salts out there that interact with, first, they take a piece of aluminum. Aluminum is it oxidizes very easily actually in the atmosphere because oxygen just kind of attacks it. Once it builds up a layer of oxidation though, that process stops. That's why aluminum doesn't just disintegrate. So what they do is they take it first into an acid bath, remove that oxidation layer, and then put it into a salt bath, which builds up a new form, this new barrier of oxide. And it's much tougher, thicker too, because it had the first layer of oxidation removed. After that's built up, they put it in a neutralizer, wash it a bunch, and out pops an anodized piece of aluminum. That anodization, there's so many different types of anodization with aluminums and steels and so forth for different coatings, like a carbide drill bit, same thing. They have some diamond drill bits now where they're actually trying to put a very small diamond coating on. Some of that's chemical and others electrical. When they deposit it on, they put it in the anode and, you know. So it's a huge area. I don't pretend to know too much about it. I only was educated a little bit on it. But we do what the requirement is. We don't have any moving parts, so we don't have to do too much crazy stuff other than these rails, because we're moving through the rails as we get ejected into space. All right, so the structure on CXB and on all the other satellites we pretty much do around here has been the clamshell 2 halves that are symmetrical, that are joined by pieces of cross. If you go look at pumpkin structures, they're very integrated. They actually use 70-75 aluminum, so it's very light. The problem is, you can't really modify 70-75. You can't do much with, other than drill a few holes in it. Okay. Enough selling structures. They're not as much fun. Everybody knows this, that we use SolidWorks to create those structures and then make sure we know where all the bolt holes are supposed to be, and then send them out to the manufacturer, have them made, and then they come back and we put them together, hopefully. Usually that doesn't quite happen. There's always some bolt hole that's wrong. All right, so on the assembly process, there's Millstar over there going under final assembly. The guys, yeah, this happened out at Lockheed where I used to work. You notice how they wrap everything in gold? It's gold-plated Kapton. And it's all just to keep stray sunlight out. You don't want to be exposed to sunlight. Sunlight's very degrading to plastics and even metals, silicon especially. The sun is pretty nasty. You need like just a sunshade, essentially. Likewise, on ours, we did the same thing, except we didn't have gold by any means. So we did copper Kapton. And that was to keep everything out from the inside, from getting into the cables and the insulation on the cables. All the sun.
You guys have massive thermal vacs and shake tables to test that satellite?
They did. They do. They do. They do.
What are they
Oh, good question. I don't know. What's interesting though on the satellites, they don't shake them in this form. This is you see here, this area in here, that's the booster, the round area. The satellite actually folded in two vertically. So they don't shake it until it's folded up and everything's tied down with explosive bolts. And then they go and they shake it. And then they do a practice deployment. It is a very large satellite. It weighs like 10 or 15 tons, something like that.
So it took a lot to get that up there.
The solar panels from Millstar were used as the basis for the solar panels for the space station.
So how old is that satellite?
It's very old. They're like 30 years old now. They're still working. Much different type of satellite. You know, they didn't have 8-bit microprocessors on there really. Nothing. Everything was radiation hardened up there. That stuff. Very neat. But you can quickly see, you know, this is a $3 billion right here, and this is 30,000.
Oh, really?
Yeah.
Was that without the CZT right now?
Oh yeah, you don't. Well, if you count that sort of thing, yeah, a million-ish. We don't count the payload because you know why. Yeah. So that is what a quick rundown of subsystems are in relation to CubeSats and all. Hopefully you learned something from this. Any questions at all? Am I supposed to let you guys leave early or something?
Great. Yeah, definitely.